So, welcome everyone to this CMOS session on developing ocean modeling capacity in Canada. We have two parts, this session now and then another session afterwards. We have 6 talks in each session. I think some very interesting presentations on a broad suite of modeling studies. So hopefully everyone will find this of interest. Just a quick announcement. If you want to put comments or questions, put them in the chat in event only rather than Q&A. We found that the chat seems to be more easier for people to respond and keep the order of questioning and things like that. And the other thing I'll just announce for speakers, since you have 12 minutes for talks, then you're 3 minutes. For questions, I'll give you a 2-minute notice at 10 minutes and then also a notice at 12 minutes. And then beyond that, we might as well get directly started. Our first talker is Martin Taillefer, who's going to be speaking on military oceanography, a collaborative way forward. Marty, whenever you want, you may start.
Yeah, can you hear me okay? Can you hear me?
Yes, I can hear you. Sorry, I shouldn't have had the mute on what I said.
Yeah, because I just had, okay, so let me share and go here. Share. Let me know when it's in full presentation mode. Is that good?
Yeah, it's good. Feel free to go whenever you want. Thank you.
Okay, let me start. So thanks very much. It's been a while since I've been involved in any CMOS. I know I've only got 12 minutes. This is not, looking at some of the presentation, it's not as scientific as it should be, but it'll give you an idea of some of the things that I'm working on. And so over the years, I've been in and out of the private sector or DFO and D&D. So I'm back in D&D, appointed as the chief oceanographer for the Canadian Forces Intelligence Command, where I'm supporting the Navy and the Air Force in terms of oceanographic and underwater acoustic support. So it's pretty much we're going to be talking about underwater acoustics, but I'm just going to go forward a little bit, just in case somebody's wondering where I exist. This is the Department of National Defense, and on the right-hand side, under the Chief of National Defense, you'll see the command levels of the Navy, and on the right is where I belong under the Canadian Forces Intelligence Command. But what's interesting is inside our organization, I belong within the Directorate of Meteorology and Oceanography. We have a very loose line of authority with the 2 different oceanographic offices on either coast. They belong to their own respective commands, so that makes our position a little less authoritarian and more of a policy sort of a capacity in supporting the fleet. So again, and I wrote it up in my little blurb here about military oceanography. Military oceanography started pretty much at the end of World War II, where there was a realization we didn't know anything about oceanography or underwater acoustics, sonar systems, and the like. And as we were being ravaged by the German Navy's U-boat program in World War II, there was a realization that we needed to do something. And therefore, during that period of time, there was a lot of growth in terms of oceanography, and essentially the Navy's provided tons of millions of dollars, billions of dollars to universities and defense labs, and essentially say, learn as much as you can with regards to oceanography, as long as you can provide some feedback to us so we can enhance our capabilities. So what has happened, and I'm giving it a bit of a military flavor here because that's what I do, but if you look at sort of a domain, my little graph on the bottom, the domain awareness, there's no scale there. But after World War II, there was a lot of growth, and this is just a fake little graph that I put, but there's been a lot of growth, particularly during the Cold War with regards to oceanography and underwater acoustics. Then the Berlin Wall happened, and so the collapse of the Soviet Union at the time, and then 9/11. And at that point, what happened is that we entered what I call an ASW doldrum. ASW stands for anti-submarine warfare. All of a sudden, geopolitically, the world politics changed, and then we became more involved in chasing terrorists than in my case, having to become more proficiency in hunting submarines. But if you look at the graph on top, after World War there was about 425 submarines lurking in the oceans. Today, there's about 475 submarines lurking in the ocean. And during this whole period, the market or the supply and demand of submarine warfare was always there, but the optics of it didn't. So why is anti-submarine warfare hard? If you look at my little chessboard here, submarine would be one of the players and the surface fleet would be the other. Obviously, it's hard to find the submarine because they're hidden. So this chess game becomes a little bit more difficult. And if you don't understand the environment and understand how sound is propagating in the water, then this chess game, I don't care how good you are in terms of an acoustic team on board the ship, you can't win this war. You can't win this battle. So it's important that we have a good understanding of the environment. And this is where I come in, is to try to impart a capability with the fleet of having a better understanding of the environment so that we can be more effective. So as a result of the doldrums and the impact to Canada has been significant. We're a very small Navy. For instance, Third Fleet of the United States, they support 75 ships. We support 7. So we've got our realm of engagement is a lot more different. But the doldrum has had a severe impact on the capability of the oceanography in the fleet, to the point that's disseminated so much that the fleet's understanding of oceanography and underwater acoustics has been completely disseminated. And I'm showing a couple points here as to how this has had an impact. So now I'm going to look into acoustic models. In terms of acoustic modeling to support the Navy, obviously we solve the wave equation and we go down to different engines, modeling engines that you see here highlighted in my little red box. So these are different types of acoustic modeling systems that accommodate different scenarios or different environmental conditions, whether it's shallow water, deep water, high frequency, low frequencies, range dependent, range independent. All these play, and so hopefully, if you have these are just engines. If you have a wrapper or package system around these engines, then depending on the environment, then the package will be able to pick out the right modeling engine to be able to get the best acoustic propagation. So essentially, the premise of acoustic propagation in the Navy is we enter data, we put it in our little acoustic modeling engine, and then it produces a sound propagation field just like you see on the bottom. And from that sound propagation field, in my case, I would produce hundreds of them to try to understand how the sound is flowing into the water and how it's propagating, and where can I best place my sensors to be as effective as I can against a submarine. Unfortunately, this slide here, I'm showing what the history of acoustic modeling in Canada, and it's been varied. And I've been involved pretty much since the 1980s and 1990s. And you see a lot of variety and different types of modeling systems that we acquired. But what's interesting, the reason I circled 1995 is the British Navy, they went with one acoustic modeling system and they stuck with it. And as a result, their fleet has been able to progress and grow with the acoustic modeling system, while we, in our goofy procurement system within the Department of National Defense, we went all over the place. And at the end of the day, our fleet teams don't have a capability. So I'm trying to get a little faster here. So right now we're exploring different acoustic modeling system, one from Lockheed Martin, one from the British. The one that says Waiter is a system that the British Navy have had for 30 years. NATO's about to produce a new system, and then the two bottom ones are the MAPS is a Canadian one, and the two bottom ones are American ones. So we're trying to get our tool sets in place so that we have a greater and enhanced capability against the submarine. One thing I want to point out, and this is where my collaboration way forward is all about. One of the things I want to point out is that D&D is an equal partner to the concepts. And concepts, while it is focused towards coupled modeling, and Environment Canada and DFO are focused on that, we in the Navy, at least me, look at concepts as a brand. There's a branding that exists under the concepts that I'm trying to expand that brand so that it has more of a collaborative role as an oceanographic agreement across the 3 or 4 or 5 departments. To me, that's important. And so with that respect, I've volunteered to be chair of the operations committee of concepts to try to add a bit of a operational flavor to concepts to support the Navy. And what I mean by that is the U.S. Navy, they've got a model, and I've been spending a lot of time down in the United States. So CMOS is the Naval Oceanographic Command. They're the hierarchy, high arching group. Then you got Fleet Numerical, who are the scientific group out of Monterey that produces all the products and capabilities that the Navy is having. The Nook is, I misspelled it. It's supposed to be an OOC for Naval Oceanographic Ops Center. The Ops Center then takes the products from Fleet Numerical and then disseminates to the fleet. In a way, in Canada, is one of the things I'm proposing this year to concepts is that while in Canada Defense we've got the Directory of Meteorology and Oceanography, I want to be able to leverage the scientific prowess of concepts and the capabilities and the products that they can produce, and to be part of an oceanographic flow of products that would go from concepts into the fleet oceanographers and then to the units. So this is sort of the end result of what I'm trying to achieve. So essentially, I know I've only got a couple minutes, but through the concepts organization, we as a Navy or through the concepts of organization, we collect data. We then pump it into the Ocean Navigator. And Ocean Navigator is a product out of DFO, which has been fantastic. I can go into history as to why this is important to the Navy, but I won't. But this is our data integrator, our data fusion and archive system that we can draw that oceanographic data into the acoustic modeling system to then become more effective and lethal against a submarine. And again, you can see this little picture, but the bottom is leveraging our partnerships, concepts in U.S. Navy and NATO to increase our capability. So just the last couple slides. One of the things I also want to do is to automate our acoustic modeling system so that we can have mini gaming scenarios. So to have the acoustic modeling system predict ahead of time, 2 minutes, 6 minutes, 10 minutes, 15 minutes ahead of the position of the submarine, so that you can understand the acoustic posture as it progresses in time, and essentially to have acoustic modeling to be completely in tempo with any ASW scenario. And you can see so at this point the advent of artificial intelligence and data analytics is going to be huge. So a Navy that is able to embrace AI in its acoustic modeling system in ASW is going to be an absolute powerhouse. But I also want to emphasize, this is one of the things I'm emphasizing to the fleet, is that the problem we're going to have in the future is underwater drones that are going to creating havoc. An underwater drone is a combination of a submarine and a mine. And the devastation could be, and any AI system that has a drone capability will be far ahead of the game. And so this is, I apologize for going a little bit sideways on this one. So this is my presentation. There's a lot of growth and a lot of capability that I need to push the fleet to be able to grow towards. And the reason I call it rhinoceros oceanography, I use my big horn to plow through all kinds of issues and bureaucracy, and oftentimes an admiral or a commander is not happy with me, and there'll be lots of blowback. And the blowback, I need to have a thick skin to be able to absorb all of that. So rhinoceros oceanography. Any questions? That's all I have. I think I made it.
Yep, perfect timing, Marty. Thank you. So people, if you have questions, please put them in the chat in Event Mobley and I will read them out. We have a question from Sarwesh. Given the rise of new threat to the importance of climate change, how can the Navy leverage oceanographic expertise to address these challenges while also minimizing environmental impacts?
That's a really good question. I'm actually part of a research group that is, from the Canadian point of view, is led by our defense lab, the RDC. So one of the things they're looking at, for example, in terms of climate change, is the impact of the ice in the Arctic that's melting, and what impact that it has on salinity in the water column in the Arctic. while this is an interesting sort of scientific uh, uh, avenue to research, for the Navy, it has huge implication because, again, salinity is a strong component of the conversion of temperature, salinity, and pressure into a sound speed profile that then finds itself in the acoustic modeling system. And what is the impact of of those changes in the Arctic that it will have on military operations? I don't know those answers, but it's something that Defense Lab is looking. In terms of Arctic climate change or any climate change activity within the Navy, I'm going to throw people under the bus right now, but I'm going to do it anyways. It's part of my rhinoceros sort of approach. The Navy at the highest level talk big about climate change, but at the managing level, not much happens. So, and that's there's a lot of commanders at sea saying this is not my problem. I've got other problems to resolve. So it's a bit of a challenge to try to educate and enhance that area of our world that we're faced with, and to try to merge both of those environmental issues and military issues. I don't know if I answered the question okay.
No, I think that's a great answer, Marty. I think for time purposes, we're going to have to move on. I threw a question in the chat. Others are more than welcome to still put questions in the chat. You feel free to answer them in the chat. And if you could stop sharing your slides, that'd be fantastic. Our next speaker is Frederic Dupont. Fred, yep, if you could just give us a second.
Something happened here. Hold on. Oh, okay, stop sharing. There we go.
Yeah, perfect. Fred, if you can share.
Yeah,
that looks great. Feel free to start whenever you want, Fred. I'll give you notice if need be.
Okay. So, well, actually, there's a link with Martin's presentation, given the fact that I'm presenting something about concepts, so concepts brand in general. We have our own resources issues, but I can show where we are at the moment. So, as Martin presented, the concept is a multi-department initiative, and we have people from DFO helping us a lot here at Environment and Climate Change Canada. So I'm not going to my slides. I'm moving up. Yeah, okay. Where's that? Yeah, okay. So I the title mentioned we're in the process of switching to CICE6 and NEMO4. So CICE6 is well advanced because we're in the process of finishing what we call an innovation cycle for the prediction systems run at CMC. And all of the coupled or oceanographic system will be using CICE6. NEMO4 is still in the on the drawing board. So the reason we want to switch to CICE6 is for better alignment with the CICE consortium. We've been lagging behind using the CICE4 version in the past. And there's definitely a lot of goodies that on the slides. I'm not going to mention all of them, but one or two important for us at the moment is the dynamic allocation, because we had to recompile any NEMO size executable in the past whenever we wanted to change the configuration, the number of CPUs, etc. So that's a big help on that side. We won't need to recompile the code every time. We'll be more flexible in terms of testing as well, and optimizing the computer resources. And the second one is the Delta Addington. I'm going to mention that later as well. So the drawback of doing this switch is in CICE4 we did a lot of change, and particularly related to the I/O, because we implemented RPN via RMN library that helps us to write directly in RPN format, which is the default format at CMC for all model product. And we also added a lot of robustness in the thermodynamics we used, especially because we decided to only use the fresh ice option of the thermodynamics. And there's a couple of more things like coupling and between NEMO and GEM required extra fields as well. So the difficulty is that we had to report all those extension except for the RPN. So for the RPN format, we decided not to do it and to stick to NetCDF instead to simplify the switch to CICE6. So all systems are obviously impacted. So that's the GIOPS, the global prediction system, GDPS, coupled CAN-CIPS, the Canadian seasonal forecasts, the GIOPS, which is the global ensemble predictions for system, RIOPS, CIOPS, WCPS, anyway, all of them. We implemented the Delta Eddington in all of them, which is a scientific innovation. And it was definitely positive for the global configuration RIOPS, but and then for the rest, it was less clear that was that positive. But he decided to go anyway along for uniform standardization of the prediction system. The other thing is that in the process of working with CICE6 and CICE4, we realized that we now have a way to couple CICE and NEMO directly on the tile, on the MTI tile level, which is very beneficial. Will save a lot of coupling issues, but it's technically quite challenging. I'm not going to give you all the details, but I can go back if there's a question about that. So the justification for the new radiation scheme is that during the previous innovation cycle, the innovation cycle number 3, we found this issue, which is this is a score of PCT, which is proportion correct total. The score has to be closer to 1 to be as perfect as possible. And the blue is the old system, and the red is the new system. And we realized that we had a degradation, severe degradation at day 5 during that innovation cycle. So and so we related that to link that to the ice thickness, preconditioning in the ice thickness, which was thinning too fast in GIOPS. And we realized that during this innovation cycle 3, we switched from the global coupled system to the global analysis system, which was unfortunately not coupled. And you see the difference on the right. So the red is the one using the coupled atmospheric system, and the two other colors are not. So basically, we realized that there was an effect of switching forcing. I guess the justification for that was that the GIOPS is an analysis cycle, so we wanted also to use an atmospheric analysis to force it, to make it somewhat self-contained instead of using the forecast. But that leads to some issues we realized afterwards. So anyway, the idea is that we want to correct the problem in the atmospheric analysis, and two folds, I guess. One is that we realized that the initialization of a sea ice in the atmospheric analysis was very different from the coupled system, because the coupled just used the field from NEMO size, whereas the GEM analysis used an open loop, its own code basically for sea ice, which was drifting away because there was no dynamics over in the Arctic. So we end up with accumulating more than 3 meters of snow, and it has impact on the short radiation that was reaching the sea ice. So So we had more radiation with the gem analysis than we have with the coupled. So that explains the overmelt we had in the Arctic in general. We compared also the short wave radiation to mosaic data, and we found about 20 watt per meter square more. So definitely an evidence that something was going on. Then we did test with Delta Eddington to prove that this was also improving or mitigating the issue. So this is we're looking at the total ice volume in the Arctic. It's just normalized by area, so it's in meters, but it's basically what you see is the weekly cycles. Whenever there's a weekly cycle's done, there's a reset of the ice concentration to the 3D ice concentration analysis done at CMC, and so this is the steps you see in blue or red here. So the idea is that the smaller the step, that means the increment is also smaller as well during that insertion. So the definitely less shock is better. So Delta Eddington was improving definitely on the old scheme, CCSM3. So that's and the area impact we see is the snow, that's equivalent for the total snow volume. And we see that Delta Eddington was also giving us, it was removing ice, melting ice slower than we used to. So definitely also mitigating this issue of a melt. So anyway, and this shows that this is after a correction that was improved. So another interesting comparison with snow thickness using the upward looking sonar in the Beaufort Sea. So the black is observation, the blue is the green is before the correction with the Delta Eddington, as the red is the new one. And anyway, we see that we have more ice, so a thicker ice with this Delta Eddington. Again, an evidence that the snow melt was reduced, and therefore also the ice melt was also reduced. We see again the impact of the jump in whenever we insert the new ice concentration. We have the step function in this. So it's doing well at the beginning, but we see at the end it's probably adding too much ice, and it takes time then to melt it. So sorry, I went back. So then NEMO4 quickly, almost out of my time now. But it was quite challenging. We had a lot of issues to resolve. We were still in the process of testing all of them. The most important is that we found out we had a lot of code change to port. Again, the same. It's still in the process, and it's painful. And preliminary test anyway shows that we have more or less the correct extent in the Arctic, but we have two fast velocities. The red is the new one with NEMO4. So we still have to address probably the turbulence in the between ice and ocean. So in conclusion, the switch is painful, definitely, and we lack resources to do that. What we would like to do in the future is if we could integrate the NEMO consortium, we'll be able to push all our extensions to them, and we wouldn't have to do this difficult job of pulsing everything together. So that's something we'd like to do, but it's, again, we're not sure we have enough resources to justify with members. We need 1.5, I think 1.5 FTE per year. But we have, at least we do that in CICE. So in CICE, we're part of consortium, and that should help a lot in the future. That's it for me. Sorry for the time.
No, your timing was great, Frederic. Thank you very much. If you have questions, please put them in the chat. I see at least one that I'm going to read out and give you, Fred, right now. So we have a question from Yo-Yu. Can data assimilation be used to optimize MOL parameters? Are there such plans in ECCC?
We definitely want to have a way to optimize parameters in ERVA, and especially for the CICE ocean coupling with drags or turbulence. So I'm not sure we will do that necessarily through data assimilation, but we're certainly going to use data as verification for when we do that. So we're thinking using a system that has been used successfully for wave modeling in our group, and basically, yeah, it's sort of a minimization error system, somewhat similar to what we will use with a cost function in a data simulation. So very close, but it's not quite a data simulation system.
Thank you. Additional questions are appearing for you. We're not going to have time to ask them live, but you can see them and respond to them in the chat if you wish. So thank you again, Frederic. If you wanted to stop sharing your screens.
Yeah, and I will leave the Zoom and go back to the actual session. Thank you. Bye.
Perfect. And then our next speaker is Dorina, Surcel, Colan. If you could share your screen, please, and unmute.
Yes, can you see my presentation?
We can see it. It's not, yeah, perfect. It's in presenter mode. Go, feel free to start whenever you wish.
Thank you very much. So I will present today the updates of the global and regional ice ocean prediction system at CMC. It's a work collaboration between the development division and the research division. So for the last 7 or 7 years, CMC upgrades all its operational system during what we call an innovation cycle. So Fred spoke a little bit about this. So now we are on the way to the end of the 4th innovation cycle. This started in June 2022, and it has a period of development test in research development, then integrated test, what we call the final cycle for some defined periods, and also the parallel pass, which will be finished next week. So we hope everything will go well, and next week all our system will be declared operational. Between this system, there are GIOPS and RIOPS. GIOPS is the Global Ice Ocean Prediction System and is used to provide the initial conditions for the coupled atmosphere ice ocean deterministic system, and also for GEPS, for the probabilistic forecast. RIOPS is used to provide initial condition for the regional ice ocean forecast, and also boundary condition and initial condition for our coastal system and for the coupled water prediction system. So if we want to look, sorry, I think my next slide. Okay, so for GIOPS and RIOPS, just a little bit about this. What I'm going to present today are actually the data assimilation system inside GIOPS and RIOPS. So I'm going to refer only at the data assimilation part. So this data assimilation part are based on NEMO 3.6 for the ocean, and now in the operational system, what is still now operational system, is CICE4 for the ice. The data assimilation is SAM2, so System d'Assimilation Mercator is based on Mercator Ocean system, a multivariate system based on reduced order extended Kalmar filter. We have also a bias correction scheme inside both GIOPS and RIOPS. So both assimilates subsurface temperature and salinity data. They are coming from Copernicus, and since November last year, we have a quality control installed at CMC, is developed by DFO. We also assimilate sea level anomalies for different satellite altimeters. We use our own SSD analysis as observations for DSST, and we blend our ice concentration analysis, which is required by CICE. So for the global system, we use the global ice analysis, and for the RIOPS, we use our regional ice analysis. There is a difference between this, not only the domain, but also the resolution, and now the data that we are assimilating in these systems. Another difference for sure is the resolution between the global and the regional domain, the vertical level also, but the initialization is done with the EIU for only 1 day for GIOPS and 7 days for RIOPS. So if we look in details at the dependencies diagrams, so I just want to show the systems, the downstream systems for GIOPS and RIOPS. As Fred mentioned before, now GIOPS and the global deterministic prediction system are changing fields. So the global deterministic prediction system provides the atmospheric forcings for GIOPS, and now we provide some fields for the ice and for the snow on ice in the Arctic. For RIOPS, we have the dependent system that I mentioned before, the coastal system, and also the waves, the coupled prediction system. If of each box has many others inside, so I don't want to go in a lot of details with this. I just want you to focus in this red circle, just to mention that each of this system, GIOPS and RIOPS, contains two weekly analyses. So the analysis window is 7 days. We have a delayed cycle and then a real-time cycle. So actually we go back 14 days. We make a first analysis for the first 7 days and then another one for the last 7 days. And with this, we refresh the daily analysis every Thursday. So what are the innovations that we propose for the fourth innovation cycle? As Fred mentioned before, it was the implementation of the CICE6 model, the update of the radiation scheme in CICE6. For GIOPS and RIOPS, we also updated the mean dynamic topography, and we added 3 new data sets for the altimeters. These innovations were done in both systems, GIOPS and RIOPS. For RIOPS, we have another additional innovations. For RIOPS also contain the regional ice analysis, and for this analysis, we use now the RadarSat constellation mission. So 3 satellites are data sets. On June 11, when our system will become operational, the regional deterministic prediction system will be discontinued. So for this reason, we had to change the atmospheric forcing from RTPS to the global system. And also we replace dependency from a forecast provided by DFO, I think, with observations of river flow at Quebec City from Canis dataset. So I'm gonna speak just a little bit about the first 3 innovations now. More details about the third one, because Fred already touched a little bit CICE6 and the radiation scheme. So the advantages of CICE6, now you know what are these advantages, so it's easier to have this new model in all our system, and especially for the next migration. And with this, the new radiation scheme, the Delta Eddington, help us to solve the problem we had in the Arctic and also in the Hudson Bay. You already saw some graphics there. I just add one additional graph here. So the first test, here are just 3 experience we have done. The first one is how our system was after the third innovation cycle. So when we lose too fast the ice. So here it's at the end of the 7-day assimilation window when we insert again the ice and we have to go back. So, but however, the ice was melting too fast. The first test we did was actually using CICE4 and Delta Eddington. And we were able to correct a little bit, but not too much. It's only when we use CICE6 and Delta Eddington, both we are able to have a better correction. So the use of Delta Eddington is good for GIOPS and RIOPS, maybe not for all the system where we change this, but for these 2 data assimilation had a great impact. Another way how we can see this impact is looking at the ice increments from the data assimilation system. So in the actual operational system, or when we use CICE4, we see that the ice increments are pretty big. But when we use CICE6 and Delta Eddington are smaller, so we are closer to the observations. So the next innovation we propose is the update of the mean dynamic topography. We need this field mean dynamic topography in order to assimilate the sea level anomalies from satellite altimeters. So currently, this field is coming from 30-year reanalysis modified by Mercator. And in the last few years, we noticed that there are many errors in this field, especially in the Canadian Arctic. And the reason why it's like this is because it's based on fewer observations in the Arctic. To address this issue and to correct the mean dynamic topography, an experiment during 4 years was run with GIOPS. We calculated the mean innovations over this period. We smoothed them and we added this at the MDT. And this experience was repeated once again. What we obtained with this, here are the example from GIOPS and RIOPS. So please take care that in the first figure is the old MDT minus the new one, and here is the opposite. So actually the sign is the same. So we add around 15 centimeters in Hudson Bay, for example. So the changes are of order of plus minus 15 centimeters. So here are the main changes in the Arctic. It's not a lot, considering that the MDT has values between minus 2 meters and maybe 1.5 meters, but is really important for our system. So here are the impact on GIOPS. So what we are looking at is a run of 1 year from 2019 March to 2020 April, where we see the difference between root mean square innovations between the new and the old system. If it's red, that means we improve the root mean square. So we improve the system. So as we can see, it's mostly red, so our system is better using the new MDT. And if we can take a look at this region here in around Indonesia, the time series is consistent with the results. So for the bias, we have a gain of 4 centimeters around, and for RMS the same, at least 2 centimeters better. So the same conclusion we obtain also for the Arctic.
2 minutes.
Arctic region using RIOPS, and the run here is for 4 years. This was also tested, the impact was also tested in the Arctic. It was the ESA Clean Arctic project where we have done more research. And if you want to see this, please go tomorrow and watch the presentation of Charlie Hébert-Pinard in session 4030. And it was significant impact on the surface currents and on the mean SSH. Also, the coastal system show significant impact on the mean SSH sea surface high. So, just to conclude, using CICE6 and also Delta Eddington help us to improve the representation of ice thickness and the snow depth, and aligns our regional and global system. The use of the new MDT improves significantly the mean sea surface high. Another innovation I didn't show here, but adding SAR from RadarSat constellation mission helped to improve the regional analysis, especially in areas where CIS charts are not available. So yeah, I think I'm gonna stop here. Thank you very much.
Great, thank you very much. Please, if you have questions, put them in the chat, and then Dorina check, and if need be, answer. I don't think we have any questions yet, and I think we should move on for the purpose of time, so thank you very much. You can just stop sharing your, yep, perfect. Our next speaker is Susan Allen. Susan, please share your screen.
Let's start at
As
the
we
beginning.
watch her talk
right?
backwards. Feel free
Yes.
to start whatever you want.
Okay, so I'm going to talk about something very much smaller scale, and including some of the geochemistry in our models. And so one of the ways that we can hope to sequester some carbon is by adding alkalinity to the ocean. And Planetary Inc. is investigating adding alkalinity to one of the Metro Vancouver sewage outfalls. And as part of this project, we looked at the Iona outfall in the Salish Sea cast model and tried to ask what would happen if you added some additional alkalinity. So I am going to give a bit of an introduction to the model, and then talk about adding the outfall to the model, and then talk about how enhanced alkalinity is added, and then I'll talk about some technical problems with this whole process and finish with a summary. Okay, so the Salish Sea cast model is a NEMO 3.6 model, and has a coupled biochemical model. We're now down to a horizontal grid spacing of 500 meters by 440 meters. And we have vertical grid spacing of 1 to 27 meters. And on the left, you can see a map. So we're out on the west coast. This is Vancouver Island here. This is the Salish Sea here. And Salish Sea cast is a model of the Salish Sea. And it's rotated, and the gray box shows the actual domain of the model. The model includes a lower trophic level biology model, including diatoms and nanoflagellates and 2 types of zooplankton. It also includes a chemistry model that models DIC and total alkalinity. And so when the idea of putting alkalinity in the Salish Sea came up, it looked like this was a very good model to take a look at what changes we could expect. And so we decided to put the outfall in, add the alkalinity, and see what happened in Salish Sea cast. Okay, so the outfall. So the outfall we worked on to start with was the Iona outfall. And there's information about this. It's a deep outfall, goes down to about 106 meters deep. It's a twin diffuser outfall. It's run by Metro Vancouver. It's the biggest outfall from Metro Vancouver. twin diffusers, and there's been quite a bit of study, and so we have something to compare to. And we can also get some data for the the flow that goes in. That's the first plot over here. So this is a climatology of the flow that comes in there, and you can see there's a big seasonal cycle because part of our rain goes into the system, and so there's more outfall in the winter. And then we can also see over here various properties that Metro Vancouver measures. We can see the temperature here. Here's the pH. Here's the ammonia, and here's the alkalinity. And so to follow what was going on, I put some dye in as well. And so this is numerical dye, so we can see what's going on. So the outfall is here off Vancouver. And inside this red box is this plan view in the center. And here at 60 meters, you can see that the water from the outfall goes mainly to the north due to the underlying currents. We can also look at it from a cross section, and it's a cross section along this orange line here. And we can see that it's hugging the bottom and it's down at 60, 80 meters. And the other thing to note here is the units here. And so 10 to the minus 2 means it's 1% outfall water in that box. And so it's highly diluted. Now, of course, if you want to do an outfall properly, you don't throw it directly into a regional numerical model. You do a Plume model, a near system model, and then you put it in. So one question was, can we actually do this, and do we get anything reasonable out of it by not putting in a proper Plume model? And so we compare to the observations. This is the first, I cut the second slide in the order of time, but we did look at more. And so on the left, you can see some data. They put rhodamine dye in the outfall, and they looked at where it came out and where it was, and then we can look at the model. The horizontal scales here are very different. But you can see that the depth of the outfall, first of all, it's hugging the bottom like it does, and we get that in the model. And we're getting approximately the right depths here. So up to about 50 meters and down to about 100 meters. And so we're doing a pretty reasonable job in getting the basic properties of the plume. And then we can look at where the plume goes in a kind of more regional picture. So this is after running it for about 3 years. So it gets to steady state in the model. And on the right, you're seeing the vertical sum in meters of outfall water. And then on the left, you're seeing a cross section along that green line. Again, due to the currents, we're seeing that it travels mostly to the north into the Salish Sea, into the Strait of Georgia, and that we can see it's an intermediate depth, stays intermediate mostly. And again, here we're seeing that this is highly diluted once we get beyond the direct sewage place. Okay, so in summary about the current plume, Salish Sea cast can characterize the Iona outfall plume beyond the near field. The residence time in the Salish Sea of the outfall plume is 500 days, and the plume is highly diluted and remains predominantly subsurface. And that was what it was engineered to do, and that's what it does. Not necessarily the best for communication with the atmosphere to take up carbon, but it does do what it was engineered to do. Okay, so the suggested addition was to increase the alkalinity of the outfall by enough to increase the pH by 1 unit. And the idea was for the pilot to run that for 1 month for 24 hours a day. This is not going to happen, but this is what I was given as a pilot addition. And so that's what we ran. Okay, so how do we do this? Well, we do this as carefully as we can because it's a very small addition. And so we're running twin models, one with the extra alkalinity, one without the extra alkalinity. In order to actually get those twin models to follow each other to a high level of consistency, we need to use the same computer, the same domain decomposition, the same versions of all the compilers. Okay, that's probably not that surprising. We need to do the restarts of the runs at the same time. That's getting to be more of a pain. And we have to check where the domain decomposition boundaries are, and it can't be too near the outfall, or again, we don't get consistency between these two models. Okay, but if we did all that, we started to get things that sort of looked reasonable. So the first plot there is showing where this 1 month of water has gone. And so it's the dye, but it's the dye only for the months that had the extra alkalinity in it. The second plot is the vertical sum of the difference in total alkalinity. And so you can see that it's positive, that's good. And it's again going where the plume goes, which is mainly to the north. Then you can see that we are getting a difference in dissolved inorganic carbon. And that means that the Salish Sea has outgassed less carbon to the atmosphere than usual. And so that there's more carbon remaining in the Salish Sea. You can see it's speckled. And that's, of course, because we're right down at the resolution here of what we can determine. And the last is a snapshot for this December 30th, 2021 of the actual difference in the CO2 flux. It's in nanomoles. So this is really, really small, but it's a reasonable looking thing. You can see it's very, very bright red here in the islands, which is to be expected. That's where strong mixing happens. And so that's bringing that additional total alkalinity right to the surface where it can have the most impact. So the differences are tiny, but you know, everything looks pretty good here on the 30th of December. However, if you go 15 days earlier, things don't look so good. And so if you look over here in this in the difference in the CO2 flux over here in Boundary Bay, you see this blue area. And that means that we've got the wrong sign. We've got CO2 flux that's going into, going into the atmosphere, which is not what we expect. And then if we go and look at the difference in total alkalinity, I put a contour on here, you can see we actually have some negative difference in total alkalinity. Now, there's ways in the real world you could have that impact, but those things are not in the model. And so I have no idea why we would get a negative delta alkalinity. And so this appears to be a numerical problem. So when I have a numerical problem, I go back to the beginning and I start looking at the very beginning and I ask, okay, what's happening? So here's my cross-section plot now where I'm showing alkalinity. And so we have the base case, we have the case with the enhanced alkalinity, and then I have the difference here. We can see the plume just as we would expect here with lots of red. So that's what we expect. But we have these little negative circles. And so when I first saw this ringing signal, I thought the culprit might be my total variation diminishing advection scheme that was working separately on the two twins. And remember, these are very, very small changes on the background alkalinity, which is a very big number, right? So the alkalinity itself is on the order of 2000, and we're looking here at differences on the order of 0.1. So I thought, okay, if it's the TVD advection scheme, things should look better if I put a bigger signal in. So in the real world, you can't put 10 times the increase in alkalinity that gives you 1 pH unit. You can't do that. That would cause sedimentation in the pipes and blocking the pipes, but we can do it in the model. So I added 10 times. And I think you can see that the only thing that's happened is that the difference has multiplied by 10 times. It is a remarkably similar plot, so we're getting a totally linear response. So in summary, the change in alkalinity is very tiny. I mean, I think you could see that as a good thing. It's not likely to impact the ecosystem very much, but it does make it extremely hard to model to get these consistent twins. We are seeing unexpected negative values. Increasing the alkalinity change by 10 times is linear. Obviously, more investigation is needed, but I'm at the point where I'd really love some suggestions.
Thank you, Susan. There's some chat questions in the chat. We may not have time for all of them. You can respond to the others later, but I'll start with the first one. This one's from Fred Dupont. Is there evidence for a return flow offshore?
So yes, there is a return flow. Generally in that region, the flow is northwards, right against that coast, and then it's southwards offshore, or basically on the other coast, on the Vancouver Island coast.
Thanks, and I guess we have time for one more question. The other question, next question from Neil Svart. Very interesting. Given importance of durability of CO2 uptake in geoengineering, do you think it would be worthwhile following things beyond the Salish Sea domain and for longer?
So absolutely, that's an important part of the stage. I cut out the slides to show how much impact there was. The Salish Sea is exporting this total alkalinity out to the open ocean, where it potentially could still take up CO2. The idea at this point is Planetary themselves are planning to run a global model and try and follow it for longer there. But it is, yes, definitely important to think about this on the long term, because very little certainly is getting used. The total alkalinity is doing very little in the Salish Sea.
Thank you again, Susan. If anyone else has any questions, please add them to the chat, and Susan, you can respond to them. There's at least one more, but I think we should move on. So if you'll stop sharing, our next speaker is Cassidy.
Okie dokie.
Looks good, Cassidy.
Looks
Feel
good.
free to start whenever you want.
All right. So hello, everyone. My name is Cassidy. I'm a master's student at UBC working with Susan Allen. And today I'm going to talk a little bit about my evaluations of a 3D numerical model of the Salish Sea in small river plume regions. So just a quick overview of what I'm going to talk about today. I'm going to go over Salish Sea cast and its model domain, talk about some motivation, get into our river climatologies versus our new method of daily rivers. And then I'm going to give an example of small river plume region model performance with the Skagit River. So as you just saw from Susan's presentation, Salish Sea cast is a 3D ocean model on NEMO framework with specific bathymetry and forcing that turns it into the Salish Sea. It includes the Strait of Georgia, Johnstone Strait, the Strait of Rondefuka, and it includes Puget Sound here in the United States. It's a highly productive coastal sea with many people living along its coastline and using its waters, so it's important for us to study and model. And then you can see this red box here that I've put on a map is the same as this red box over here, which is our model domain, just to give you a bit of orientation. So here's a quick snapshot of our top-down view of the Salish Sea. We have grid points in X that go from 0 to 398, and grid points in Y that go from 0 to 898. If we zoom in a little bit, we can see that our horizontal resolution is about a ½ kilometer square. And if we look at a side slice, we can see that our vertical resolution is variable. So in our shallower depth intervals, we have about 1 meter resolution. And then we can get up to 27 meter resolution deeper than 100 meters. So with the Salish Sea being so important to so many people, there are a lot of general uses of Salish Sea cast. First, general insights into the Salish Sea's dynamics, chemistry, and biology are beneficial. Salish Sea cast can help give guidance on government and private projects, like we just saw with Planetary. And then there's a number of public tools, things like spring diatom bloom forecasting and storm surge forecasting. But my model use is a little bit more focused on answering questions that are specifically related to the river forcing. So 1/3 of my research is freshwater tracking with model dye. So if I have a river runoff here at this star, which I hope you can see my pointer, if I put a bunch of synthetic dye into it, I can watch where that dye goes see where it accumulates, see how long it resides in certain regions, etc. Another one of my current projects is doing clustering of coastal salinity, temperature, and pH to assist in study plans for some ecologists. And then what I'm going to talk about today in this presentation is doing model evaluations that are specific to small river plume regions. And these small river plume evaluations are important because in addition to the larger scale evaluations of the model, we want to consider our specific regions and process scales. So now we're getting into our old method of river climatologies versus our new method of daily rivers. This plot here on the left is just a snapshot of river discharge for one day, where each of these red points represents some amount of river discharge going in. This large one here is the Fraser, and I'm going to call that large, and then I'm going to say it's too large, and I just want to focus on the small ones. So as you can see, we're still left with quite a few rivers going into our region, which gives us this challenge, which is that we have more than 150 small rivers in Salish Sea cast, but not all of the rivers that go into the Salish Sea are gauged. So we're not getting real world flow data for all of these rivers. Our old solution to this problem was monthly climatologies for river flow. So this lighter line here is our river flow for our old model. And you can see, like I said, it's this monthly climatology. But the thing about doing it this way is that we don't have any day-to-day variation associated with rainfall or snowmelt or other weather events. And we also don't have year-to-year variation. So if 2019 had a particularly wet January and February and 2020 did not, we wouldn't capture that in our monthly climatologies. That brings us to our new solution, which is using our daily rivers based on weighting of other gauged rivers in a shared watershed. So that's what's shown in this darker line here. We have daily variations because of weather, and then I'm only showing 1 year here, but I promise you that if you looked at a bunch of different years for our input here, they would be different year to year because it's based on real world. So now coming into doing some evaluations of this new method, I've done some more focused analysis on 11 rivers around the Salish Sea. And just a quick summary of what I found in terms of comparing our model salinities to observational salinities from DFO, PSF, ONC, and IOS. For the root mean squared error up here, I have an RMSE that goes up to about 4 grams per kilogram here. And then I have a bias that goes from about minus 0.7 grams per kilogram to positive 0.7 grams per kilogram. But this can be a bit overwhelming to look at, so let's focus on one river for now. I'm going to choose this gadget because it's interesting because it has our highest root mean squared error over here. And also because we improved the bias here from much too salty to somewhat too fresh, but we did also noticeably increase the RMSE when we moved from our old model to our new model. So as I showed before, this is what our river forcing looks like now in this darker blue line. And then I also want to show that from our old model to our new model, we did change the bathymetry, which inadvertently closed this little channel here. So we had this that used to be connected, and now in our new bathymetry, it's closed off. So to look more in depth at these statistics, we can do a little breakdown by season here. So if we look at the RMSE on the left, we can see that it increases overall, but it increased slightly more in the spring and summer. But overall, it's now still pretty uniform. And then if we look over here on the right at the bias, we can see that it actually flipped signs for all of the seasons. So each season, if it used to bias too salty, it now biases too fresh, and vice versa. So now I want to look at some plots where I have observations on the X and model values on the Y for all of this data that I've done these statistics with. Right away, I want to point out that we can see that the salinity varies from about 2 grams to kilogram to about 30. So looking back at our values for RMSE and our bias, the bias is pretty good relative to the range, and the RMSE is not terrible either. But really the things I want to focus on for these plots, the first thing is that in our old model here, we can see that we have this systematic error where this red line is fitted and tilted quite up. But we can see that this isn't present in the new model, although we have increased the scatter here. And the second thing I want to highlight between the old model and the new model in these plots is that in the old model, we don't actually produce any salinities that are lower than about 15 grams per kilogram. Whereas luckily in our new model, we see those close to zero salinities in both the model and the observations. So now looking into trying to explain those changes that we're seeing, focusing on the root mean squared error, we have a couple of educated guesses for what's going on in here. And I'm still looking into confirming them. But we're thinking that this slight increase could either be due to something temporally. So if we're increasing all of this variability here in our new daily river scheme, if we have any kind of time offset there, obviously we're going to introduce more error. But it could also be something spatial. So you remember I showed that our new bathymetry changes our area quite a lot. So if we're incorrectly capturing our new plume dynamics, or that closed off channel is causing a difference in our plume, that would also increase our error here. Now, moving on to the bias. To understand this, I'm just going to point out that a positive bias means the model is too salty, and negative bias means the model is too fresh. And if we look down here at this bottom time series plot of our new model minus our old model for flow, we can see that we are putting less fresh water into the domain in the summer and more in the other seasons. And this pretty clearly explains this flip-flop in bias. But overall, the bias is now more uniform across the seasons as opposed to having this really large in the winter and lower in the other seasons. So just to come back to this, again, I want to mention that the scale of our errors is compared to a range of salinities from maybe 0 to about 35 grams per kilogram throughout all of these regions. And our bias improved for 6 of the 11 rivers that we evaluated, and our root mean squared error improved for 8 of the 11 rivers that we evaluated. And just to offer some concluding thoughts, Salish Seacast has been overall improved by our new daily rivers method. This is shown in both the small river plume region evaluations that I showed and some larger scale evaluations done by Susan. But obviously there's still some work to be done in specific river plume regions. And then my final thought is that understanding the strengths and limitations in river forcing methodology by doing things like this can facilitate not only Salish Seacast specific science, but also general coastal oceanographic modeling science. So thank you.
Great, thank you very much, Cassidy. If you've got questions for them, please put them in the chat. While we're waiting for any other questions in the chat, I might as well, oops, no, sorry, someone else beat me, so I'll ask you a use question first.
Okay.
Are runoffs, and actually it was going to be the same question as me, are runoffs still introduced as rain at the surface or as some other form?
Yeah, so we have our little boxes where we've, called our river mouth, right? And that is still the way that it's being introduced. But the actual river runoff now is not just based on like a rainfall climatology. So the method of introducing it into the model is still rainfall into a little box, but it's not based on rain, if that makes sense.
It's a better estimate of the value type of thing, even if the approach is. And do you have enhanced mixing at the river mouth, and if so, over what depth range?
Yeah, that's a good question. I'd have to confirm with Susan. I don't think that for all of the small rivers we do that. There might be something happening different in the Fraser, but I can confirm that and then put it in the chat.
That would be great. Thank you very much. So, not to get any more questions at the moment, I think we'll move on to our next speaker. So we're also good be having another talk related to rivers. Tahya, would you please share your screen? Looks good.
Oh, there we go.
Please start whenever you wish.
Okay, sounds.
We just
for
lost your
today.
sound,
And I'm
Tahya.
gonna. You lost my sound?
Yeah, now you're back.
Oh, okay. I didn't change anything, so hopefully it stays. Okay, I'm going to be talking more about temperature in rivers in the Arctic today, and I'm going to be looking at how we can force ocean model simulations in the Arctic using river water temperature forcing from hydrological models. So as a little background for Arctic river runoff, so rivers are a very important source of fresh water in the Arctic Ocean. By volume, the Arctic Ocean is around 1% of the world's ocean, but it takes around 11% of the world's river runoff. So a really large proportion of river runoff goes into the Arctic Ocean. And this runoff is increasing with climate change. As you have the hydrological cycle speeding up, there's more discharge going into the Arctic Ocean, and as well as you have more melting of mountain glaciers and permafrost and such. And so that's shown here. We see the discharge increase that we've observed from the 1980s. And as the discharge increases and air temperatures increase over these catchment regions, we get also an increase in the river water temperature itself. So we have more river runoff going into the Arctic with climate change, and we have warmer river runoff going into the Arctic. We have some observations at some of the major rivers complexes in the Arctic of the river water temperatures. So this is from the Arctic Great Rivers Observatory here. And so this is all of the temperature gauges, the temperature readings that they have for the 5 major rivers in the Arctic Ocean. So the Colma, the Lena, the Mackenzie, the Ob, and the Yenzi. And you can see there's some pretty big gaps in the time series here. So we have, for instance, here from around 2007 to 2010, we don't have any temperature readings from these large rivers. And even throughout the time series, it's very temporally distributed when we have temperature readings of the Arctic. So we have some idea of what the temperature is, but we don't have a complete record of it. And this poses a problem if we want to add this information into ocean models, because ocean models require more consistent time series of river water temperatures in order to force it. And as well, we only really have this data for the larger rivers, and there's lots of smaller rivers into the Arctic as well, similar as in other regions in the Pacific Northwest. This is, there's lots of smaller rivers that go in, which we don't have any temperature gauge information for. So this gives a question of how do we represent the effects of rising river temperatures in ocean model simulations when we don't have complete records from observations, or from climatology can be quite then biased or sparse. So I'm going to talk about doing this using hydrological models. So for this work, I used the output from the AHYPE hydrological model, which is run by the University of Calgary. And they run it for the continental Arctic and Hudson Bay catchment region, and they produced river runoff data, discharge, and temperature from the 1980s up into 2018 for what we're using here. So I've just compared it here, showing with the AHYPE in the blue for these different regions, compared with Dine-Trenberth, which is a very commonly used river runoff data set for forcing ocean model simulations. And so an advantage of using this hydrological model is that we have a lot more interannual variability within it compared with other data sets like Dine-Trenberth. We also have higher discharge. So if you took the sum of these boxes for the high Arctic here, you would see that there is a larger amount of river runoff going in with AHYPE. And as well, it represents more of that climate signal that we've seen in recent decades because we have that interannual variability with it. So this is for discharge. So if we look at in terms of temperature, how the AHYPE data does at some of the major rivers. So I have here the Ob and the Mackenzie, so the two temperature gauges that they have from the Arctic Great Rivers Observatory, compared with the AHYPE model. So AHYPE is in blue again, and then in yellow is we have the observations. So we can see that we have a kind of similar seasonal trend between the two data sources, with this kind of peak in the summer around August or July, and kind of tapering off in the shoulder seasons with low water temperatures in the winter. The AHYPE data does underestimate the temperature that we see in the observations. This could be for a few reasons, other than just it could be too cool coming from AHYPE. We also have the observations are point observations, like taking out one gauge. So how that point trends across the whole river complex, which there's a much like lower resolution when we talk about it in the AHYPE data, so it's going to be more distributed. Can also affect this, but we do have an idea of we're getting a similar pattern that we want to see in these water temperatures, and if anything, results we'll show later will be underestimating the heat flux that we get from rivers as opposed to overestimating, which is probably a safer assumption to make. So if we look at this river water temperature from the hydrological model in terms of heat fluxes, we can see this is for our major regions in the Arctic here. And we can look at the heat flux from each region from these river water temperatures. So our highest heat flux comes in the Cassidy. So this is where we have the Ob and Yenzi coming in. So this makes sense. This is the highest volume flow region, so we get the highest heat flux in this region. And then we also have very high heat fluxes coming from the Mackenzie and from the Laptev Sea region. So these river complexes are producing a large amount of heat, and this is generally not included then in ocean models. And we're going to look at now what happens when we add this into an ocean model simulation. So we include these river water temperatures. So for this work, I used a version, NEMO version 3.6, run at a 1/4 degree resolution. So this configuration is called NEMO4, so Arctic, Northern Hemisphere, Atlantic. You can see in our region of interest here, we have a resolution of somewhere between 8 to 15 kilometers for the high Arctic. It's a forced ocean model with a couple, forced atmosphere model with a coupled sea ice module. I'm going to look at using two different sea ice modules, LIM2 and LIM3, and I'll talk about more why in a second. We use CGRS for the atmosphere, and we run the model from 2002 to 2018. So here we're going to look at, this is the difference between the two ocean model simulations, one run including these river water temperatures and run one without the river water temperature input. So we can see this is the heat content in the top 100 meters, and this is the difference for 2017, so towards the end of the time period. We can see in the Central Arctic, especially on that coastal regions, we do see an increase in the heat content slightly when we include river water temperatures, which is what we would expect to see. We see a slightly different behavior here over kind of north of Europe, where we actually see a decrease in the heat content in this region, which is kind of interesting. So we know that there's some large scale changes, but let's look at this in terms of the shelves itself and where those river waters come in. So this here is for the Cassidy. So this is where I showed there was the largest heat flux coming in from the river water temperatures. And this is again the difference between the two model runs. So a positive here is meaning that there's more heat content when we add in the river water temperature, and a negative would be less when we add the river water temperatures. So this difference here, we can see is generally positive throughout the time series, and is very seasonal, which corresponds with what we're doing in the model of as we add the temperature in the summer, we have these warmer water temperatures. We get these spikes in heat flux in this, and then in the winter, this change kind of tapers down. And it's a fairly consistent change across the different shelf sea regions. What's interesting, though, is the difference in this change. This change seems to differ depending on which sea ice module you use. So on the left here, I show it with that LIM2 sea ice module. This is the plot I showed before. And on the right here, I have it with LIM3. So LIM3 compared with LIM2 is a multi-category sea ice module as opposed to LIM2, which is just a single category. It also includes things like land-fast ice and other more complex sea ice representations. So when we add in a more complex sea ice module, we get a slightly different response in the heat content, especially towards the end of the time series, where we start getting these kind of decreases, even in the summer months, of the heat content between the two model runs, where we have like a decreased heat content in the sea ice module, in the LIM3 model runs. And just a more complicated response from the ocean. So if you look at this on the large scale, so this is a question. So what do these heat content changes that we're seeing from this change in river flux mean for sea ice? So we can look at this on the large scale here. So this is the seasonal change in the sea ice between those pairs of model runs. So the LIM2 model runs and the LIM3 model runs. And this is for the fall 2016. We're going to look at here because for the seasonal cycle is we have this change more in the shoulder seasons. So for LIM2, when we have this more simple sea ice module used, we can see quite the response in the sea ice. We see this kind of on the shelves, we get these kind of like thinning patterns of sea ice here in the heat content runs, but in the runs with the river water temperature. But towards the straits, especially around Greenland here, we actually see an increase in sea ice thickness when we use when we include the river water temperatures. So this could mean that as more heat content is added, the ice pack is more able to move and more ice is being transported out. We see a similar pattern with LIM3, but it's much reduced, this response. So as we have a more complicated sea ice representation, we see less of this kind of increase of transport and thickness out of north of Greenland here. And the similar thing of lower sea ice concentration on the coast, but just a smaller response in the ice mod, depending on the ice module used. So I'm running out of time, so I'll just quickly show my conclusions. So river runoff can be a significant coastal heat source in the Arctic, but it's generally not represented in ocean models, often from data availability. So we looked at using hydrological model output to include the river water temperature effects. This consistently seemed to affect the heat content in coastal regions. I showed it for Cassidy, which is the largest river complex, the largest river flow complex, but it's also true in other coastal regions. And this likely has further effects on sea ice, especially when considering the complexity of sea ice that you include and these interactions between sea ice and heat content, depending on categories and other factors. Thank you.
Great, thank you, Tahya. I don't see any question. We do. And that's a question from Yo-Yu. Do you also use temperature for the glacial runoff at this point?
No, this is just for all the temperature changes are for the continental Arctic. We don't have any temperature from Greenland or anything. All of that comes from, all those discharge data is just from the Bamber 2018. So it's only any of the changes for heat content are constrained to the continental Arctic.
Although I've been told the next version of HYPE will include temperature from runoff and temperature from glacial sources, but we don't have access to that. Yeah. Have a next question from Natasha. Have you looked at the changes in the sea ice velocity and export out of the Arctic?
Yeah, that's something I've been working on. I didn't have anything to show from that yet, but that's one of the next steps that I'm doing right now is looking at changes in transports and export, which seems to change, like from preliminary what I've seen, it does seem to change, but I didn't have anything to show for it yet.
One more last question for Fred Dupont. How is the data set river temperature verified?
Yeah, so it has been verified for the discharge amounts, like the AHYPE data set. It's Trisha Stadnick's 2021 paper, but for temperature, it hasn't been. So that's kind of some of the stuff I was showing here. So I have I've been taking just some observations from the Arctic Great Rivers, RDAT, and then there's a few other smaller ones for some of the Canadian rivers, and just trying to compare them with they have point to point, as close as possible, because they're from such like gauge locations for these like large river complexes. So it's been slightly challenging to get accurate observational comparison, especially with the amount of data that is available from observations. But basically, this is the verification we've done for temperature so far.
Great, thanks, Tahya. There's more questions in the chat you can look at, but I think we're at the end of the session. So I want to thank all 6 speakers again for very interesting presentations. And everyone, I think, has 20 minutes till our next session, which starts at 2:05 Eastern, which would be 12:05 Mountain, 11:05 Pacific, and I guess there's people in Atlantic, which would be 3:05, and I'm not going to add the half an hour for Newfoundland. If you're there, you can do that yourself. So thanks again to all our speakers and everyone, and look forward to you in the next of our sessions, where we've got 6 more presentations.
Paul, just a quick question.
Yeah.
After I finished talking, I was never able to see the chat. There seems to be like another chat room.
Did you
that I was
open the
never able to
Event
see.
Mobley app where you go to see the talks if you're not in presenter as a presenter?
Okay. Was
There's
there
a whole
any
bunch of questions for you in there.
Okay. Yeah, perfect. Thank you.
Okay. And I have a question for you, Wendy. For us who are chairing the session, is it the same Zoom? We can stay here, or do we need to go out and back in? I'm going to assume I'm staying here because I think it is still a Zoom B link for our session. For those of you who are speaking, I guess, Tahya, Cassidy, and Dorina, since you're finished, you can log out whenever you want and join the audience for our second session. And the 6 speakers, or I guess the other 5 for session 2, can log in here, please. Thank you.
Thanks, Paul, for doing that. You got people pretty much on time. When were you giving them the 2-minute warning?
I was giving them officially at 10, but sometimes if it looked like they were about